Well, thank you. Oh, well. All of that rambling was lost. Right? It just went off into space. Okay. All right. So let's take a look at the modulation transfer function again. Remember, we looked at that. And this is the relative, amplitude of the spatial frequencies that our system will pass. And as we go out in cycles per millimeter, it rolls off, and there's our system, right? These other systems, can be described by different modulation transfer functions. And normally, manufacturers of imaging equipment, particularly computed tomography, will actually give you some kind of indication of what this function is for their system. And if they're trying to tell you that their system can image very fine structure, not only will they show you clinical images of, say, the inner ear, where you see these extraordinarily fine structures like that little stirrup thing and everything, like these tiny structures are well resolved. So they'll show you that. But then they'll show you the modulation transfer function. And we'll say, our modulation transfer function is much higher at these higher frequencies than everybody else, right? Sometimes they'll just give you one value on this function. They'll give you a value of the spatial frequency at which this gets down to a certain level. And depending on the manufacturer, they'll decide what that important level is, whether it's 10% of the maximum or, whatever. So you need to read those actual numbers carefully, because they'll say, oh, we have a cutoff of like 19 cycles per millimeter. And you're like, oh yeah, but you're down to 0.1% or something at that point. But anyway, that's how systems are often characterized, right? And we can look at this example. This happens to be a magnetic resonance image here of space, like this is GXY, and this is the Fourier transform of this function, okay? Oftentimes when you display a Fourier transform, you take the log of the value, because the dynamic range of these numbers is quite large. So the numbers around the origin are much, much bigger than the numbers out here at high frequencies. So instead of plotting it as with, a linear scale, you'll do a log scale, right? And this is probably a log scale. And this is the magnitude of the Fourier spectrum. So we see this is, spatial frequency in X, spatial frequency in Y. Normally the origin is at the middle, and that is the DC value, or the average value, right? So the point right in the middle of the Fourier transform, remember, this is when in the Fourier integral, the K value is set to 0, right? So this is just the integral under the image. That's all this is, right? And so that point there gives you, if I integrate this image, how much stuff is there in there? That's the middle point. It's called the DC value of the Fourier transform. And then everything tends to roll off after that, unless somebody has arranged this image to be reset such that that integral is 0. Right? So you can imagine you could do that, right? You could rescale the thing so that you had positive and negative numbers. Anyway, so here's a Fourier transform of this picture. Let's multiply it by a modulation transfer function to turn the Fourier transform into this function. And what we've done is we've taken one of these modulation transfer functions and multiplied down the high frequencies and kept the low frequencies. Right, so all the low frequencies here are identical. As we move out to higher frequencies, they're actually forced down. We just multiply them to be a smaller number, right? And then this is what the resultant picture looks like. So this picture is equivalent to convolving this picture with the Fourier transform of this filter, this modulation, right? That's what you get, is this picture. And then if we modulate even more aggressively and we cut down higher and higher frequencies, eventually we have very few high frequency looking objects, no edges, sharp edges are gone, little points, individual pixels are gone. The whole thing gets blurred out. Okay, so it's out of focus. Yeah.
So when we have a patient or someone in the scanner, do we get out the Fourier transform of the whatever we're trying to take, and then we convert it to our image every time, or is that the other way?
So the question is, when the patient is in the scanner, say this patient is lying in the scanner, do we measure the Fourier coefficients of this picture as our raw data? I just paraphrased your question. And the answer to that is yes, we do. In magnetic resonance, the actual raw data itself is here. We just sample across here, right? And we build up this matrix of data, usually one row at a time, sometimes 3 rows at a time. You know, there's a whole bunch of tricky ways to do this. Sometimes you spiral out and sample this function, etc. And so you'll find Tom has some great lectures on how this is accomplished and the trajectories you can take through the Fourier space to try and measure this image with the highest fidelity in the shortest amount of time. Right? In CT, it's a little different, but we do eventually use Fourier coefficients sometimes. There is a way to, as we'll see with CT, there is a way to reconstruct the object by taking an inverse Fourier transform of projection data. Okay, and it's called the projection slice theorem, but we'll get there. So yeah, this is our raw data. So you can imagine I can make this picture in a lot shorter time because I have really a lot less data to measure to get this picture versus this picture. And the other issue is that these values are actually exceptionally small. And so the ratio of that measurement value to the underlying noise in the picture can be not so great, right? And so whereas here we've got a lot of signal to noise to get sort of the large, features of the image. Okay, any other questions about that? So this picture, you should sort of have it in your head, right? That if I have a sharp image, I have a lot of Fourier coefficients. If I have a blurry image, my Fourier coefficients are closer to the center, closer to the DC value, the average value. Okay, I think that, yeah. Okay, so the question is, if we have the Fourier data that we've imaged with MR, what does that Fourier data directly tell us about some medical or physiological condition, right? That's essentially why we're in the course. We're gonna figure that out. It's like, how does this data get modified by, say, flow, right? So if you're taking a MR image of a heart, it's not just a static object. This data will actually be changed by the fact that the blood that you're imaging is flowing, right? Other things will be like, if I'm sampling this Fourier domain here and I take 10 milliseconds to get all my samples across here, but the object I'm imaging, the signal decays away very quickly, right? So as I'm sampling, the actual amplitude of that signal is decaying away. And so what that will do is it'll affect how I sample this Fourier transform. I will have this multiplication of a decay across the raw data. What does that do to our picture? So that's another reason why we need to know where the raw data is, how the physiology and the physics of the experiment, the measurement, are affecting the look of our raw data, or the relative amplitudes of all these points. Sometimes the amplitude is the same, but the raw data gets phase shifted. and that happens with flow, for example, or movement, like if the patient's breathing. And then here's some other things, like say I'm taking a picture of a patient and their chest and they're breathing, okay? When I look at a pixel that's right near their chest wall, as I'm acquiring this raw data, that pixel will blink on when they breathe such that their chest wall intersects that pixel value. And then when they exhale and go down, that pixel essentially blinks off. So now my raw data for that voxel is like a blinking signal, right? It's not a constant signal that's just modulated by all of my gradients and things like that. It actually is something that's coming and going. What does that do to the picture? You know, and so we'll see that what that does to the picture is it makes multiple copies of that voxel up and down the picture. It's pretty interesting. Okay, any other questions about? Yeah.
So here, why do we decrease the high frequency content here? Because the resolution of that one is
right. So the question is, why would you ever use this data when you have this data, right? And I have a couple of answers. One is if you want a really high signal to noise measurement of like 2 by 2 by 2 centimeters in this person's head, right? Then this data has higher signal to noise for that measurement than this data, because we haven't introduced noise from all of the stuff out here. All right. So if I have a low resolution measurement I want to do, I should match my image acquisition, my data acquisition to that resolution, right? If, on the other hand, I want to, in this patient's pituitary, see that there's a little bright spot that's like 3 pixels by 3 pixels, and it's significantly brighter than the surrounding stuff, and that's important to find, then the last thing I want to do is this, because I will just smooth that signal right out and I'll never see it, right? So for that application, I really want to push the high frequency so that I can see that small object, right? So it's like a matching of what is the size of the thing you're trying to detect, what is the precision of that measurement. The other thing about doing this is that I can do this really fast. In fact, I can make a picture like this in an MR scanner in about 20 milliseconds. This takes 2 minutes. So if I want an image that tells me, where is this patient's head in the scanner? Like, is it moving? You know, or are they, maybe I take one of these, like a 20 millisecond shot that just tells me where the head is. And that way I can, so if the head's going like this, I take a 20 millisecond shot, oh, the head's over there. Now I can adjust my high resolution data with the knowledge that the head moved this way, right? And so oftentimes you'll have monitor images, and in breathing this happens, you know, when you want to see where all the organs are going when the patient's breathing. So you monitor the motion with low resolution pictures that are taken very quickly, right? And MR can obtain resolution which is virtually unmatched, right, by other imaging techniques. It just takes a long time, right? So you have to average the data over and over, and you have to get out to these large Fourier dimensions, like high spatial frequencies, right? And that just takes time. So if you have a half hour on your hands and this patient can stay perfectly still, you know, like to within fractions of a millimeter, then you can make an unbelievable crystal clear picture of this person's head, right? Like, on the other hand, if you look at how the brain vibrates, well, it doesn't really vibrate, but how it pulses with blood pressure. So when you generate blood flow in the brain, it actually moves the brain a little bit. You ask, well, how much? It's, you know, half of a millimeter, stuff like that. So the question is, why take an image with 10 micron resolution when everything's like pulsing, you know, by that dimension? So you got to fit all these things together. We often, like, we did a project where we had people who had died from sudden cardiac arrest, and they had donated their body to science. So we had these hearts of people that had died from sudden cardiac arrest. And we put the heart in a jar and we put it in a 3 Tesla scanner at the NIH. They have lots of time at the NIH, and it doesn't cost $750 an hour like it does usually at a university. So we imaged that thing for like 2 days. Just imaged and imaged and imaged and imaged. And that was absolutely spectacular. I'll show you a couple of pictures, but it brings to light things you just don't normally see, right? And this happened in the brain when people started doing 7 Tesla images of the brain. Stuff emerged that you just don't normally see. So hence why people want to go to 13 Tesla and things like that. You might see something you've never seen before, right? So it's very exciting. Okay, let's PowerPoint. Here you go to sampling. Okay. Okay. So we're going to now look at the question of if I have a continuous function and I want to make a picture of that function, how finely do I have to sample it? Okay. And this is related to lots of things in life. But for example, if I have a straight line and I want to characterize that straight line over some domain, right? And tell you what its value is at every point X in that domain. I don't need to sample it at many points, right? If I can sample it really accurately, basically I just need 2 points and it defines it everywhere on that domain, right? But we know ahead of time it was just a straight line, right? So if I have a function that is really wiggly and has lots of changes in it, then I have to decide, well, how often do I have to sample this thing in order to give you what we could say is an accurate representation of that function, right? And what does that even mean? So, this is the boundary between the digital world and the analog world. Our functions that we're measuring usually are analog functions, essentially. So in X-ray, if I shoot X-rays through a patient, and then right before my detector that's detecting the shadow that the patient's cast, you can assume that that shadow in space is a continuous function, right? You could sample it down to arbitrary resolution and you would still, see, it would never quantize itself, right? Similarly, for a patient who's emitting radio frequency energy in an MRI scanner, the way you encode where that energy is you put a continuous magnetic field gradient across the patient and you get different frequencies out. Those frequencies are continuous. They don't come out in finite buckets, right? It's a continuous spectrum of radio frequency energy. So we have analog signals to begin with when we have our underlying function, which we've been calling fxy. This is the thing that's going into our system. So most of the time it's analog, right? And what we're going to do is digitize that signal such that we will replace a function. If I have a analytical function, I can tell you that this analog signal is, well, that's great. Oftentimes I can't, but I'm going to replace it with a finite number of values of that function sampled at some interval. This makes life easier because when I ship that function to somebody else or I put it into my computer to reconstruct, all I have to do is transmit these values, right? So now I've just got a list of values and that's my function. That's the representation of the function. And then you can imagine that if these values themselves are highly correlated, you can compress that list and then reconstruct it just using standard compression techniques, right? So a lot of transmission of data between parts of scanners, if there's a lot of data, you can imagine there's a lot of research going into how do I compress this data, right? Transmit that and then decompress on the other side, right? And I think everybody's, Google and everyone else is saying, well, if I want to put a picture up on the screen, what's the minimum amount of numbers I need to transmit to get an accurate picture, right? What's the best form of compression there? When you guys use your camera, right, on your phones, nowadays it's like, I forget, it's HEIC, I think compression is what it is. And it used to be, the standard compression used to be JPEG compression. When you look at details of those pictures, when you zoom up, you can start to see how that compression has messed up some of the spatial relationships, right, in those pictures. If you just look at your camera image, say you have a Nikon or something, and you just save raw TIFF, it will just save the value of every, pixel on the detector. And it's an enormous file. It's usually 16 to 24 bits or something deep per color. And the spatial resolution is the spatial resolution of the detector. But because images are smooth, so if we have an area like this, I don't need to save all of these numbers. I can save kind of the information about the slope, or I can save the differences between neighboring pixels, stuff like that. And you can compress it down pretty successfully. And so JPEG is one thing. This HEIC compression is pretty good, actually. If you should save, with your little camera at home, you should save some. It's like, I don't know if you can save raw TIFF, but do JPEG, HEIC, and all this, and then zoom up on somebody's eyeball that's in the background of a group shot and see what it does to their spatial relationships, right? So anyway, that's what's saved, are these numbers, okay? You save that in a file, and it's like a TIFF file, a JPEG file, or whatever. So here's a image of a chest. So this is a patient's chest. This is their sternum right here. Lung is here. Down here, this is a bit of their spinal cord, or their cerebral spinal bones right here. And then this is the descending aorta. This is the ascending aorta, okay? It looks like a very clear picture, right? So it's a CT image of an axial cross-section of a patient. And the pixel values, the brightness represents the relative amount of attenuation of the X-ray at that location in the patient. Okay, that's what it means. So if it's bright, that means a lot of X-rays got stopped there. If it's dark, that means a lot of X-rays just went straight on through. Okay. So if we zoom up and take a look at that picture, we start to see some, details in the encoding of the data. One, you can see that the noise structure here seems to have kind of a wavy, wormy kind of background structure. It's not just random white noise. Like if I draw a line across here, each subsequent pixel is not just totally uncorrelated with the pixel before it, right? There's some kind of structure to that noise. That's one thing to observe with this. The other is that this is the left atrium, and this is the left atrial appendage up here. This is the wall of the left atrium. That's pretty impressive. I don't know if you guys have ever looked at images of hearts and things like that, but getting that clarity of a very thin tissue wall, which is the wall of your left atrium, is quite impressive. Don't get spoiled, because most scanners don't produce this kind of image. Now let's zoom in farther, and you can see now there's an artifact here, and the artifact are these little squares, right? And the squares give you the dimension of the voxel that was used for the reconstruction, okay? And so this is an analog of saying, what is my comb function, right? The comb function is the distance between the center of each of these squares, because across a square, all we have is one value, okay? So that's a value at that. A sort of first order approximation to the spatial resolution of this picture is often given as the dimension of these squares. Okay, so you say my voxel dimension is, and it's like, 0.1 millimeters or something like that, right? However, if you're responsible and you reconstruct these things appropriately, you should have many more pixels inside the true dimension of the spatial resolution of the scanner. You shouldn't have the pixels be at the spatial resolution. You should have those pixels be smaller so that you can see if I had a tiny object and it made a blob, I could actually visualize the blob. It wouldn't be just one pixel, right? So you want to be able to do that. But anyway, we can look at how this is digitized, right? If I use those values at the center of each one of those squares, and I produce a picture that has many more pixels, right, in between. So I convolve it so that I'm now on a much higher resolution display. I get this picture. Okay, and so now you can't really see the squares anymore. The squares are so small that you basically don't visualize them, right? This is a more accurate representation of what is there, right? When you look at this, you say, huh, this patient has very interesting physiology, and then they come in little cubes, right? Yeah. And so here, that is sort of the underlying, best estimate of the object that we can get from this resolution. When we draw a line across, let's go back to our squares, and we get a single value at a certain displacement, the function looks like this. Okay, and these are the numbers. Here's our grayscale values, right? And they're usually integers, right? Stored as integers. And it just gives a value for each one of these squares. And that's the thing we store on the computer, okay? When we do it with a higher number of pixels or smooth it, this is the function, and it's probably a more accurate representation. Okay. Any questions about that? Yeah.
So in these kind of pictures, how do you determine if, for example, an artifact versus, for example, a calcium deposit, like something that could actually be problematic?
That's a great question. And so, you recognize something about this picture. Let's go back to the larger field of view here. So this is the ascending aorta. This is in this slice. It's a very thin slice of the patient. In this slice, the left coronary artery comes into the slice and then out of the slice. Okay, and so this is the patient's left main coronary artery. Okay, so that's coming off the aorta in a slice, either up or down from here. This little bright signal here actually is a physiological thing. It's not some random signal. It's a chunk of calcium that is now embedded in the arterial wall of this patient. Okay? And this is everybody develops coronary calcium, and your vessels actually calcify as you get older. So you all, if we imaged you with CT, a couple of you would have coronary calcium or calcium in your aorta. If you image the professors, they all do, right? Because it basically just happens with age, right? And the risk is, like, if you develop a lot of it, it's an indication that your vessels are undergoing these injury healing, and it's a higher probability that you will actually have a heart attack if you have a lot of this stuff. It doesn't kill you, but the fact that it's being generated at a certain frequency, it indicates you're doing things that will kill you, okay? So that signal, so the question is, like, how do you know that's not an artifact, right? Well, that's a great question. Take a guess. Like, why would you call that an artifact? If you were to call it an artifact, how do you know?
I guess would be you take multiple photos, and if it doesn't appear, and average it over, and if only some of them are like signal distribution.
Right. So idea there is, well, if this thing shows up time and time again, consistently, then we know it's a true signal. It didn't just show up in one picture, okay? An equivalent way of doing that is saying I take all those pictures I took and I average them together. Now my signal to noise is really high, right? And if this was, for example, a noise spike, which happens, right? Then perhaps we would get it wrong. We would call a noise spike a piece of calcium. And that we'll see, I'll show you some examples where it's a toss-up, right? But for this one, you can measure its area, right? It's not just a single pixel. So you have the area and you have its amplitude divided by the random noise, which you can measure out here. So the random noise level of this scan, if I take a box here and measure the root mean square deviation out here and ask the question, how many root mean square deviations is this thing? If it's 8 times higher than the noise level, the probability of that being noise goes down to about 0.001, right? And you just say, okay, it's not noise, right? Artifact's a different thing. Artifact, in MR especially, you can generate some very interesting looking signals that can actually mask as physiology, and you have to be aware of those artifacts. Here, it's pretty hard to generate an artifact in CT that looks like this. In CT, you get used to artifacts, but what they look like are streaks. They're mostly streaks and blurs. If this thing's moving, you'll see it'll have an arc where the streaks will come off of it. This is a particularly beautiful picture. It doesn't have any of those problems. This is done with this was done at the NIH about 4 years ago with what then was an experimental scanner that had a detector with the detector elements had been cut in half, their dimension were cut in half. So instead of 1 millimeter separation between detectors, there was a 0.5 millimeter. So this was a very expensive proposition, right? Because you're multiplying your number of detectors by 4 and you've got a lot more data and stuff, but it produced these incredible pictures. It's really nice. So let's go back to sampling. And here's a picture of a sampling function, or two sampling functions. The one on the left, the one on the right. The one on the left, we're going to sample our function f of x at each point in the xy plane, and the distance between our sampling is going to be delta x and delta y. So this is a two-dimensional sampling cone that will now represent this image with the values at these points. Okay? Obviously, this is significantly undersampled, right? We're going to, if all we had were those voxel values, the picture we get would be a very poor representation of what was there, right? So we change delta x and we make it smaller, and we derive a new sampling cone and then sample with that one. And so our job, right, as imagers and designers of equipment is, what does delta x and delta y have to be in order to detect what I want to detect? And two, can I just build a system that has the minimum delta x and delta y possible, right? And so so eventually we'll have, you know, this delta x and delta y be down at fractions of a millimeter and have very clear pictures. But mathematically, we're going to describe that with essentially a comb function with these distances between the delta functions, right? And those are called the sampling periods. This is just out of Princeton Links in chapter 3. And we're going to, you know, to do mathematics of sampling, Dr. Prince spends quite a bit of time developing the math of what a comb function is and how you extract or sift out discrete values from an underlying function. And, you know, so we're going to convert from our continuous function f to a discrete function that is essentially just has values at a finite number of points, right? To get there, we're going to go through creating delta functions or delta comb functions that will extract this thing. Okay. So 1 over X and 1 over Y can be thought of also as the sampling frequencies, right? They're essentially in inverse centimeters and inverse millimeters or such. So in computed tomography, this type of sampling comes up absolutely directly. Unlike, we'll see in MR, it's slightly indirect. But in computed tomography, if I have an X-ray source at this tiny dot here, and I shine X-rays towards my detector, and my object is here, and I raster my source across my object, okay? When I build my detector, I can do 2 things. One, I can have a single detector element that tracks with the source and just measure, you know, what the transmission is between the source and the detector. Or if the mechanics of that becomes horribly difficult to achieve, I can just move the source quickly and have a set of detectors already in place. And this is the way CT scanners work now. You have a set of detectors that are just sitting there in place, and you have a lot of them, right? Instead of rastering across here, we can have a single source that shoots X-rays in a fan beam. So it covers the entire patient, right? With one shot. So I can go poof, like a flash bulb, and then make an X-ray flash, and then have a fixed detector detect all of those transmissions simultaneously, okay? So now we're getting really fast, okay? And that I had to, you know, move this across, and that was in the first CT scans. That's how it was done. Now we're going to flash a CT and get essentially a projection through the sample. And then I can go in the 3rd dimension, and I can just stack a bunch of these detectors, right? So that I have one of them here and then a stack on top like this, flash my X-ray and get essentially a 2-dimensional picture, right? It's a 2-dimensional shadow of what's there. And we can use that to create CT images of multiple slices through the patient, right? And so the sampling rate that we're trying to decide on here is the balance between the cost of putting 1 million detectors here versus 1,000 detectors here, right? And if I put 1 million detectors, I would have very, very narrow detectors, and they would be spatially localized very accurately to within, you know, a millionth of this linear dimension. But I wouldn't get many photons in each detector, for one thing, right? Because a lot of detectors just wouldn't see a photon if we keep the dose down. And the efficiency of packing these detectors is such that, you know, you have sort of an optimal width of the detector, and then the stuff that goes between each detector to avoid crosstalk between the detectors. So there's some kind of efficiency there, and it's usually about 90% efficient. 10% of this thing is stuff between the detectors. If you did 1 million detectors, that 90% would drop significantly, because it's hard to make that stuff smaller, right? So that's how we're going to figure out. Normally, it's just the cost and the physical structure itself that determines how many detectors we have here. Typically, in a CT image, you know, you'll see there's about 1,000 in this direction and 64 to 256 in that direction, something like that. The geometry of this detector and how it's set up in a scanner in which the source rotates around the patient looks like this. You have an X-ray source. It pushes out this fan beam, okay, of X-rays. Normally, it doesn't flash the X-rays. Normally, it just keeps them on constantly. And so it just produces this beam of X-rays that's just always on while you're taking your data, and then it shuts off. So it's on for a couple of seconds or a fraction of a second, and then it shuts off. When it's on, you are bathing the detector in X-rays, which have contrast information because it's a shadow of the patient that's sitting in the scanner. And so this whole thing's going to rotate around, right? So here's our sampling rate problem is on this arc right there. If you open this up and look inside, this direction is in the Z direction of the scanner. So if I shoot an arrow through the donut hole, the arrow would go this way, right? So the patient's head is up here, the patient's feet down here, okay? And then the patient's left arm would be over here, right arm over here if they're lying on their back here. Okay? So this is across the patient or around the tube, and then this is head to feet. And so these, now they make these detectors such that they're modular, and they just put them together like Lego stacks and then chonk them all in as a big Lego machine, right? And inside each one of these is a set of these detector chips here. And so this is the Z direction or head to foot direction. And we're just looking at this thing here, and we're looking at it along this way, right? And then these chips, when I look at the detail of what one of these chips looks like, you pull it out and it's 16 by 32 individual detectors. Okay? And those are separated. The centers of those detectors are usually about 1 millimeter apart. Okay? And that chunks in, and then we just make our detector that way. And this is in this, again, in the Z direction, right? And we put a whole group of those together. I put this back down in there, and then I have all of these. And I think in this scanner, it works out to 832 samples in that direction and 256 samples in this direction. Any questions about that? So when we're sampling, when we've decided, okay, that's the samples we need, we have to look at the function, which is our continuous function, which is the image. So right before the detector, if I look at the density of X-rays as a function of space and say X and Y above the detector, that's essentially a continuous function, okay? And so that's, say, this pink line here. What's going to happen is at my detector locations, I am going to get samples of that function. Two things happen. One, I decide where I'm going to sample a function, and then I also decide on a width that I integrate the amount of signal that's coming from that function, right? So, the X-ray detector has a width, and so any X-ray that enters the detector along that width, we're going to add that up as signal. So I have a sampling rate this way, and then I have the sampling width. Right? We're going to approximate this function with these numbers. And the question is, how do I know that I have enough samples along here to adequately represent this function? So one way of describing that would be, am I able to, with these finite values, reconstruct the continuous function with exceedingly small error, right? So can I, perhaps I can even reconstruct the continuous function exactly, right? If the continuous function doesn't have abrupt changes here in between points, then there's a high likelihood that I can reconstruct that function from these points exactly, right? And so that's what it means to be sampled adequately. Right? So what happens if we don't sample adequately? We're going to generate artifacts in our picture, and we'll look at those artifacts. And the fundamental question is, can you reconstruct that original continuous signal just using the samples, right? And so the trivial example I gave before is if this continuous function was a straight line, we certainly could reconstruct that function exactly, right? If I knew a priori it was a straight line. Normally it is not a straight line, right? Think about what this function would be in computed tomography. As I move along in space, if I hit the patient's spine, projection of the spine, all of a sudden the function drops down substantially because many fewer photons are being absorbed, right? So I have an abrupt edge there. So I need to be able to sample that, yeah.
So the detector is usually like squares or rectangle piece, right?
Yes.
With like a surface area. And so let's put it, it's getting like some amount of photons, like an n number of photons. Do we sample the number of photons as like how many photons it's getting, or is it like more like if it's above a threshold that detects that?
That's a great question. So I'm going to repeat the question so that folks online can hear. So the question is, if I have a X-ray detector element, and it's say 1 millimeter by 1 millimeter, and it's sitting in my detector array, and X-rays impinge on that element, and I measure a signal. And the question basically is, what is that signal, right? There's two ways to do it. One way, and it's the most common way, 99.9% of all scanners do this. You have a material that when X-rays impinge on that material, they cause light, right? So it's like a fluorescence or some other interaction that causes light, right? And then at the bottom of that detector, which usually has reflecting surfaces inside a column, you'll have a photodiode which counts up the brightness of the light, and that's your voltage. Okay, so that's the intensity of the X-rays that were measured for that measurement. Okay, and the issue there is if the X-ray itself has higher energy, because we'll see we have multiple energies come out. If it has higher energy, the light will be brighter, right? If there are more X-rays, also the light will be brighter. And so that's what you're doing. You're integrating up all the X-rays causing the light. The light turns on and then decays away with a certain time constant. And so it glows for a very short period of time. And so you'd like your detector to glow for as short as possible so that you can sample with high temporal frequency. There's another class of CT scanners which are now becoming available. They were just basically experimental units up until last year. But now you can buy a commercial CT scanner, actually from Siemens, that it's called a photon counting system. And so instead of using light, it uses a material that directly reacts and produces a voltage based on its interaction with an X-ray. And not only that, it will give you a voltage that is dependent on the X-ray energy. And you can essentially, for each individual X-ray, if the fluence isn't too much, if you don't saturate it, you can measure what its energy is to within a certain accuracy. Normally they bin it into, say, 3 different energy categories or 4. So it's not super fine resolution in the energy dimension, but it is high energy versus low energy or middle, right? So that detector, one of the really cool things about that detector is that you can just get rid of photons that aren't in the energy range that would have come from a direct path through the patient. Okay, you know that if this photon goes through the patient and this is your energy spectrum, if it's much lower than that energy, they just throw it out. It's just scatter, right? So that's a photon that went in, bounced, and then came out, right? So your ability to reject all that scatter is much better. And you can also make pictures of different energies. You can make a high energy X-ray picture and a low energy X-ray picture to get sort of a balance of contrast between a photoelectric type of interaction versus a Compton scattering, right? So that's the X-ray detector. Okay, in MR, the interesting thing is when we're sampling an MR signal, it's not a projection really of the patient that we're sampling. It's radio frequency energy. And so it's in the time domain. Okay, so when you have your coil in MR, you have a radio frequency antenna that is above the patient or very close to what you want to image. And then you create a signal in the patient, the nuclei inside the patient, mostly hydrogen nuclei and water or fats, give off this radio frequency signal, right? And you image it with an antenna. So you think about that for a minute, you go, well, this is a non-starter. How the heck do you position radio frequency energy with this goofy antenna I have in my hand that doesn't have any kind of focusing or anything other than just its sensitive area here, and the radio frequency is coming from all different places, right? So you would get a bright blob just under your detector, your antenna. So it turns out it isn't the intensity as a function of position that you do use with MR. You measure the phase of the RF coming out, and the phase of the RF, like how it's shifted in time with respect to the transmitted signal, tells you precisely the displacement of that signal in one dimension, right? So you do that multiple times. So for magnetic resonance imaging, we sample a time domain signal. So look at this example here. We have seconds across here. So this is 150 milliseconds. And I have a signal that's like oscillating in time, right? With a certain number of frequency components. I can sample these points here are a plot of points that were sampled at a particular rate. So a particular delta t in time, okay? And there's my function. In order to analyze this data, we're going to take the Fourier transform of that data, right? And when we take the Fourier transform, we can see here's our frequency in hertz, right? That is represented inside this signal, right? And this is the relative amplitude or power spectrum at a particular frequency. So that's when I'm sampling with this rate, okay? Now let's take every 8th sample. Say I have a receiver that this one sample this high was too expensive. So I got a cheaper receiver and it can only sample this fast, right? In the radio frequency realm, right? So I'm gonna get a sample at every 8th point. We know this function sampled at this rate. When I take every 8th point, it looks like this function. And when you take the Fourier transform of this function, ask, well, what frequencies are in here? You get this. This, when you look at it, is a heck of a lot different than this, right? There's no question something's going on here. We lost some information when we dropped our sampling rate and took every 8th sample. There's stuff going on that we are not sampling appropriately, right? Because the Fourier transform of this thing looks entirely different than this. In particular, it looks like a set of functions that are just repeating themselves over and over. That's the first thing we notice, right? Is that, wait a minute, this feature is just repeated. So what's going on there? And then when we look at this function, it actually looks like it's reflected around some point. So basically we have many fewer points in the Fourier domain that are characterizing this signal. Okay. In fact, a factor of 8 fewer points in the Fourier domain, which makes sense, right? Because we had a factor of 8 drop in the number of points that we're characterizing this signal. So when we get together on Monday, we're going to talk about this, what this is, and we're going to get to a statement of the Nyquist criterion, which is how fast do I have to sample something in order to sample it sufficiently to characterize the signal as I want. And that's going to be called the Nyquist criterion. Okay.